Thank you. Hello, everyone. Let me just get this ready. Now everyone knows how long my password is. I usually get it wrong a few times, too. This time I got it right the first time. Yeah. All right. Let me just get a... Is there a visible timer, or shall I just get my... No, I can just use my phone. It's maybe more convenient. I'm going to try and talk for 35, 40 minutes and then leave some time for questions as well. All right. So the topic of this talk is generating music in the raw audio domain. And this is something that I've worked on for several years at DeepMind. And I'm going to try and motivate that work a little bit and show you some of the results that came out of that. So first, a little bit about myself. So I am currently a research scientist at DeepMind here in London since July 2015. Before that, I was a PhD student at Ghent University in Belgium, where I worked on extracting information from musical audio signals, so learning feature hierarchies for musical audio signals, and then using those for classification, genre classification, artist identification, music recommendation, and things like that. And in that context, I did an internship at Spotify in 2014 in New York about music recommendation and sort of using audio waveforms in the recommender system so that it can also recommend music that hasn't really been listened to before, so where we can't really rely on data from previous listening sessions. In my stint at DeepMind so far, the first few months were spent on AlphaGo, because when I joined the company, that project was sort of in full swing, so I had the opportunity to do a little bit of work on that. Simultaneously, I was also kind of ramping up and getting to know all the systems, so I didn't actually end up contributing that much, but they were kind enough to put my name on the paper anyway, which was really nice of them. And then after that, we moved on to WaveNet, because we were, at the time, a colleague of mine out of the north, who some of you might know, was working on autoregressive models of images, and they were starting to work really, really well. And so we were looking at where else can we sort of apply these ideas. And we decided together to try this on audio. Obviously also on speech signals, which is arguably a commercially more interesting application. But personally, I was more passionate about applying this to music and trying to generate music directly in the raw audio domain. And so that's what I ended up spending a lot of time on. My online coordinates are there as well, so I have a blog that I haven't updated in a very long time, but there are a few blog posts about some of my previous work there that are still relevant today, I think. My personal email address is on there as well. If you have any questions after this event or any comments for me, feel free to contact me there, and I'm also reachable on Twitter. So brief overview of my talk today. So first I want to motivate a little bit why I think it's interesting to model music in the raw audio domain. And then I'm going to tell you a little bit about WaveNet and what this model looks like. And then I'm going to tell you about my efforts to generate music with the original form of that model and what came out of that. And then the second part is going to be more about more recent work where I tried to scale these models up so that they could model long-term correlations in audio, because obviously in music you want to capture correlations across many seconds, maybe even minutes, to sort of create a coherent whole. And then finally I'll show you some samples from these models as well. So first of all, why model music in the raw audio domain? Typically, music generation is a task that is studied in the symbolic domain, because we have good symbolic representations of music, like scores, for example, but also maybe lead sheets for jazz, or a slightly different flavor of this, or you could just have a melody which is just represented as a sequence of notes. There's a lot of different sort of gradations and symbolic representations of music, and typically when people try to build models to generate music, they will use one of these representations because it makes abstractions of a lot of things that are maybe initially may seem less relevant. And there's one particular representation that is very commonly used in this context, and that's a piano roll. And it's a very old representation. As you can see here, it was also used for player pianos back in the day. But these days, it's more often used in its digital form, where, for example, music producers use this to compose music sort of directly in this form. But it's also a very natural way of representing music for generation, where you can sort of treat it as a time series with many dimensions. But I think actually that modeling raw audio is interesting and is something we should try. And this is because all of these high-level representations make abstraction of a lot of things that I think are actually very interesting and very important for our interpretation of music. Music sounds a lot more musical when it's performed on real instruments rather than when it's a computer sort of generating sine waves. And this is something that I want to try and capture with my models of raw audio. So many instruments, and a guitar is a very good example here, they have quite complex action spaces. And what I mean by that is that the player of the instrument can affect the timbre of the instrument in various ways. So on a guitar, for example, you could play with a pick or with your fingers. You could vary your picking position. Obviously, you can use the frets to play a different pitch, but you can also play harmonics using these frets. Hammer-ons, pull-offs. There's just a lot of different techniques that all have sort of their unique sound. And so capturing all of that variety in a symbolic representation is actually really difficult. And I would wager that we haven't really succeeded in that at all. And so the piano is actually a bit of a counterexample, because on a piano, if you have this, you can kind of completely capture the sound that the instrument will produce. Because the only things you can do on a piano is you can choose which keys to press, you can decide when to press them, and you can decide how hard you're going to press them. And so we can sort of capture all these quantities in this representation here. But for a guitar, I think we cannot do that. So it's a little bit ironic that actually most of the examples that I'm going to show you are actually piano music. There is a pragmatic reason for that, which is that I was trying to collect data sets of sort of single instruments from YouTube. And on YouTube, it's a lot easier to find a lot of solo piano music than it is for any other instrument. It's also the instrument I'm most familiar with because I play the piano myself, so that's sort of why I use this as a starting point. But the techniques are general enough that they should also work for other instruments, and I'll show a few examples of that as well. So let's talk a little bit about WaveNet, which is an autoregressive model of raw audio. This is a paper that we published back in 2016. Actually, it went on archive then, and it never really got submitted to any conference, so it hasn't really been peer-reviewed. At this point, I don't think we're going to do that, but it's sort of an interesting tidbit of information. We kind of really wanted to get this out there quickly, so that's why that happened. So in WaveNet, we're going to try and model waveforms, audio waveforms directly. And so first we need to represent them in sort of a computer-friendly way. As you know, sound is a pressure wave, so we can represent this as a one-dimensional wave. And then to represent it on a computer, we need to discretize it, both in amplitude and in time. And this moving diagram sort of shows that discretization. Like at the full zoom level, you can see sort of the individual samples popping up. And so this is 1 second of audio that we've sampled at 16 kilohertz. Which means that the highest frequency that we're going to be able to represent here is 8 kilohertz, which is actually on the low side for music. It's fine for speech, but for music, it sort of diminishes the perceptual quality a little bit. I stuck with 16 kilohertz regardless, because obviously increasing that significantly would also require larger models, and I wanted to be able to train them in a reasonable amount of time. And so this is one of the reasons why the quality, the audio quality of the generated samples that I'll play for you is maybe not optimal. So yeah, we're going to try and build a model of these waveforms, and we're going to try and do next step prediction on them. So given all these samples, predict what the next sample could be. And to sort of account for the human perception of volume, which is logarithmic, we're going to do the sampling of the amplitude in a non-uniform way. So we're going to use something called mu-law quantization, which is actually a very commonly used technique, for example, for telephone codecs as well, because it sort of maps better what the human ear maps out better what the human ear cares about. It cares about detail if the amplitude is low, if the volume is low, and it doesn't care so much if the volume is high. And so this is kind of an important step that made this a tractable modeling problem with the hardware that we have today. And so once we have our sampled waveform, we can stack our WaveNet model on top. And WaveNet is really just a convolutional neural network, but it has an interesting structure where at the input side we have just raw waveform sample. So we have this 1D sequence that I showed you before. And then at the output, at the top of this diagram, we actually have the same sequence, but we shift it one time step so that the model is trained to always predict what's going to happen next in the signal. So our input is also our target, so to speak, but shifted by one time step. And then between the inputs and outputs, obviously, we have a sequence of hidden layers. And between those hidden layers, we're going to ensure that all the connections are causal. And that means that we want to make sure that our model doesn't cheat and is not able to look into the future and basically just copy values from the input to the output. And so that's why you don't see any arrows here going to the left. So all the connections are going up or to the right so that the model is causal. Now, in this sort of toy diagram of the model, obviously real wavenets are bigger than this, but nevertheless, in this toy diagram of the model, when we predict the last sample of our signal there at the right, we have a receptive field of 5 samples of the input. So what we can see from the input is only the most recent 5 samples that we've generated. And as you recall, I said that we're sampling the waveform at 16 kilohertz, or 16,000 hertz, which means that 5 samples is actually less than 1 millisecond of audio. So this model is not going to do a very good job at predicting what happens next because it just doesn't have a large enough context. And so the typical thing to do in deep learning when you're faced with that kind of problem is you just stack more layers, right? Just make the model deeper. But here, if we want a receptive field of, say, a few hundred milliseconds, that means we're already going to need hundreds of layers to be able to achieve that. So it's not a very cost-effective way of doing that. And so we use a little trick called dilated convolutions. This is not something we invented, but we thought it would work great for this, and that turned out to be right. We sort of stretch the convolutional filters that we have as we go higher up in the model. We basically start skipping time steps. And the result of this is that we're going to get this connectivity pattern that's shown here, kind of like a binary tree, where sort of higher layers are aggregating information from progressively longer timescales. And this turns out to work pretty well. Of course, this sort of tree structure is still shared at every time step because it's still a convolutional model. We're basically just skipping some connections, but it's still a convolutional model. And that was sort of the key ingredient that started to make this model work. Sorry. I have a slightly different diagram here of this connectivity structure because I wanted to show a few variations of this that we tried. Because obviously you can have this binary tree structure, but you can try and do other things and see how they affect results. So here we have layers and time steps going from left to right, and then layers from bottom to top. And so this is one of these trees. In practice, what we do is we repeat this tree structure a few times. We don't just have one tree. And this turns out to be very important. So in this toy example here, we stack the same tree structure of 4 layers 3 times, and then we get 12 layers, and our total receptive field of this structure actually becomes 46 time steps, because for each tree that we stack, you kind of have to take into account that these trees are replicated at every time step. So actually, the connectivity pattern that we get looks like this, but that's obviously quite messy. So usually I draw the diagram like this. And the reason this repetition is important is because it creates many different computational pathways for information to flow through the network. If we have no repetition of the tree structure, and we look at each pair of input and output time steps of the sequence, X and Y, then there will always be sort of a single pathway through this tree, like the one shown here. But if we stack multiple trees on top of each other, we have multiple pathways. So you have this pathway between X and Y, but this one is also a valid pathway, and so is this, and so on and so on. So suddenly you get this exponential number of pathways between inputs and outputs, and this seems to like having at least 2 repetitions seems to be very valuable for these models. And then there's a few other things that we tried, like increasing the filter size of the convolution, but not the dilation, creates this structure that's actually no longer, strictly speaking, a tree, because you have things that are sort of connected in multiple ways. Interestingly, increasing the filter length from 2 to 3 and not changing anything else doubles your receptive field. So it's kind of like a cheap way to get double the receptive field, because you do 50% more computation over the whole network, but the receptive field is twice as large. So this is a trick that I used for the music models, and that seemed to help quite a bit there. Of course, you can also change the dilation and the filter length to get sort of these more spread out trees that have the receptive field grow much faster. Now, once we have these models, we can train them on a bunch of music scraped from YouTube, and then interesting stuff happens. So I'm going to play a few samples from WaveNets trained on different sets of data. And so, yeah, I have these on the slides, but maybe I'll play them locally, because I think the internet might be a little bit slow. So this first one is going to be a model trained on a data set called Magnetagatune. It's sort of a standard data set in music information retrieval research. And it's basically a collection of contemporary music from lots of different genres that is available under a Creative Commons license, I believe. So you can sort of do this kind of stuff with it. And I trained a fairly beefy WaveNet with a receptive field of about 1 second on this data. And here's what that model produces. So it's kind of all over the place. It seems to like drums, so you get sort of these drum solo type sounding things. And it kind of makes sense that it would do that, right? Because the receptive field is 1 second. And the reason I've trained a model with a receptive field of only 1 second is basically that's what I could fit on the hardware that I had. And this is at DeepMind, so you can imagine the hardware that we had was actually quite decent. It's just that the activations in the network end up taking so much space, because you have 16,000 input time steps, and then you compute, say, 512 features for each, and then you have maybe 100 layers that are computing these features, and you have to keep track of all of them to be able to backpropagate through the network and train it. And so basically this model maxed out the memory of a typical modern GPU at batch size 1. And so this was about as far as I could scale it. Still, I thought this was a cool result, but it doesn't really sound like music. It can't really be called music. And so next, I tried simplifying the problem a bit by restricting the data set to a single instrument. And this is sort of the data set that I ended up doing most of my work on. And this is piano music from YouTube. And you may have heard a few of these before. So here the model is capturing the sound of a piano very well. It's also understanding roughly what chords sound good and what notes sound good, but how to fit them together, it hasn't quite got that. And that's, again, of course, because of this receptive field that's too short. I have a few more. So I also trained models on guitar music. And when you look for guitar music on YouTube, most of what you find is sort of flamenco style. So that's reflected in what the model produces. So what's interesting is that this sounds a little bit more coherent than the piano to me, but it's actually the same model. And what I put this down to is that on a guitar, there are certain chords and notes that are easier to play than others. And so I think sort of the composition space is a bit more restricted, and the model picks up on that. So it picks up on chords that are more common than others and then tends to produce those. And that makes everything sound a little bit nicer. And then finally, we also tried training this on string quartets. So here the model is actually capturing multiple instruments at the same time, and it does that quite well too. All of these are also available online. I will share my slides on the Meetup website as well, so you can check out the full set of samples if you want. So that was satisfying, that worked. As an aside, around this time, I also set up a collaboration with the Magenta team at Google Brain. So they're a team in Mountain View, California, who are interested in building things with machine learning that are useful for artists. Not just music, just artists in general, but they do happen to have a lot of people that have a background in music, so most of their output has been focused on music so far. But so they're interested in building stuff for musicians to play with. And so one thing that we did together was build a conditional WaveNet that's also an autoencoder to do timbre modeling. So in this model, we feed in the audio both through the WaveNet to do next step prediction on it, but also to an encoder that sort of maps it to a lower dimensional representation, and then we condition the WaveNet on that representation so that it can do a better job reconstructing the original waveforms. And then we have basically a latent representation of our audio that we can start manipulating. Like we can interpolate between different sounds, or we can jiggle the various latent factors and sort of see what happens. And there's a blog post, there's a paper about that, and there's also a blog post about that on the TensorFlow website, strangely enough, but that's where the Magenta website lives. And then sort of onto what I did next. So as I said, it was kind of satisfying that the model is able to capture all these instrument timbres quite well, but I actually wanted to make it produce music. And that means capturing long-range correlations and modeling things, like producing coherent melodies and chord sequences and things like that. And so I had a paper late last year at NeurIPS titled "The Challenge of Realistic Music Generation: Modeling Raw Audio at Scale," and this is about that. So this is my work on extending the receptive field of WaveNets beyond this 1 second threshold that I could fit on hardware before. And so I've always said actually that an alternative to doing this project would have been to just wait 10 years and then train a massive WaveNet on the hardware that is available then, and that would probably also have worked. But so this is a slightly more clever way to be able to model long-range correlations today. And so this paper is also available on arXiv. So we're going to first talk about dilation again, because as I explained, when you do dilation, you sort of get this much faster increase in your receptive field. Actually, you get an exponential increase in your receptive field when you add layers to your model, because every layer that you add will double it, right? So intuitively, it seems like you should just be able to train a WaveNet on longer sequences and have it capture longer-term correlations just by adding a few layers. But as I also hinted before, you actually run into this memory issue, because the memory usage of the model during training is still going to be linear in the receptive field length, even though the model depth is now logarithmic in the receptive field length. And the reason for that is precisely because these intermediate activations that the model computes have to be stored in memory to be able to do backprop. There is actually quite a lot of recent literature on doing sort of recomputation of the activations instead of storing them. And we haven't tried to apply that to WaveNet, and I think that would maybe also work. So that's maybe an idea for future work on this. But in any case, without that trick, you basically cannot scale the model up indefinitely using dilation. So you need something else. And the trick that we came up with to do that is to use discrete autoencoders. So we basically take the WaveNet, which is this blue triangle on the right, and we extend it with a few additional building blocks. We have an encoder that also takes in the waveform and is going to learn a discrete higher level representation of the waveform. And then we have another block which I call the modulator, which sort of maps this to biases for each layer in the WaveNet and sort of tries to make the WaveNet do its bidding. So given the higher level representation, this will encourage the WaveNet to sort of reconstruct the original waveform that corresponds to it. And so this is basically an autoencoder with main differences that the decoder is autoregressive, it's a WaveNet, and also we have this quantization bottleneck because we want discrete intermediate representations. There are two reasons why we would want that. One is that it sort of inherently limits the capacity of this high-level representation, so there's like this many bits that you can store in it and nothing more, and this is actually useful because we kind of want to make abstraction of all the details in the waveform that don't actually matter too much for human perception. And so this is one way that allows us to do that. And another reason is, of course, that WaveNet is a model of discrete sequences. So if we want to build hierarchical models, which is what we're going to do, it's much more useful to already have a discrete representation that we can just train another WaveNet on. And so that's another reason why we have this quantization bottleneck. We explored two variants of this. So we explored VQVAE, which is vector quantization variational autoencoders. So there you sort of learn a code book of latent vectors and quantize them during training. And I'll explain a little bit about how that works. And then we also, for this paper, actually explored an alternative model called the argmax autoencoder because we ran into some stability issues with VQVAE training. And we found an alternative model that sort of also works, but not quite as well. But it is much more stable. So there are situations in which you might want to use that. So in VQVAE, you basically have the standard autoencoder structure with an added vector quantization block that is going to quantize the outputs of your encoder, which I call the query here. And that gives you a way to sort of represent the sequence of codes as an integer sequence as well, which is nice. And then what goes to the decoder is not the unchanged query, but rather the quantized query. So you sort of only give it a quantized version of what the encoder's produced. But other than that, it's just a regular autoencoder. And the way this works is best illustrated with a few diagrams. So imagine that the encoder produces a d-dimensional output. And so these outputs live in a Euclidean space. And we are going to quantize that output. So we learn a few sort of canonical representations, codes, call them here. And those are indicated by the red dots. And we can also order these codes and give them an index so that we can represent them as integer sequences. And then our encoder will produce some real-valued vector in this space, which we call Q. And then we quantize that to the nearest code, Q prime. And then this is what goes to the decoder. And then simultaneously, we can also say the encoder produced the code corresponding to index 6. Now, how do we actually train this? Because backpropagation requires that everything in your model is differentiable. And obviously, this discrete quantization operation is not differentiable. Turns out we can just ignore it and pretend it didn't happen. And that works perfectly fine. This is called straight-through estimation, where basically in the backward pass, we're going to pretend that what we sent to the decoder was actually Q. And then we can just backpropagate and pretend nothing happened. For this to work, it is obviously important that the distance between Q and Q prime isn't too large. And so we'll add a few losses to guarantee that. So we have our, it's an autoencoder, so we have our reconstruction loss. But we'll also add a loss to learn the codebook on the fly during training. So we sort of learn the different codes in the codebook. And then we also add what's called a commitment loss. And this is going to ensure that when the encoder outputs a latent vector corresponding to a certain code, it's going to try to continue doing exactly that. So it's going to try and commit to the codes that it outputs. And this guarantees that the codes and the outputs of the encoder won't move too far apart, and our straight-through estimation trick still works. So the alternative that we came up with to deal with some instability issues in this model is the argmax autoencoder, and it's actually really similar. Except here that the encoder is just going to output a bunch of real values, and there's no real codebook to speak of. So we're going to output a bunch of real values. We're going to apply a ReLU to them so that they're all positive or 0. Then we're going to normalize that to 1. So it becomes kind of like a softmax, but it's not quite a softmax because we have these ReLUs in there instead of exponential functions. And then we just do an argmax on this. and then pass that to the decoder. So now we directly have this integer representation. And then obviously, when we backprop, we pretend that this argmax operation didn't happen, so that's what it has in common with the VQ model. The loss function for this model is quite similar, except that we don't have this codebook loss because we don't have a codebook. And instead, we have a diversity loss, which is going to continuously encourage the model to keep using all the different possible discrete outputs. If you don't have that, it's just going to collapse straight away at the start of training and not learn anything useful. This is sort of a general downside of putting non-differentiable stuff in your model, is that you have to add all these tricks to actually make it work with differentiation. An alternative interpretation of the argmax autoencoder is that it's basically like a VQVAE, but with a fixed code book, where the code vectors are just one-hot vectors. And then once we have these discrete autoencoders, we can stack them into hierarchical models, and this is sort of the key idea in the paper. We can actually learn higher level representations of our waveform and then sort of repeat that procedure multiple times to get a hierarchy of higher and higher level representations. So at the bottom here, we have our waveform at 16 kilohertz, and then we map that to a code sequence at 2 kilohertz. So we have a downsampling factor of 8. And we chose to use codes with the same bit rate as the input signal. So our input is 8-bit audio at 16 kilohertz, and our code signal will be 8 bits at 2 kilohertz. So that means that there's a factor of 8 compression going on. And then we repeat that procedure once again to get another factor of 8 compression. So in total, we're compressing by a factor of 64. And now we have a sequence of symbols at 250 hertz. And then on top of that, we just train our regular WaveNet like we did before. But now it's being trained on these high-level code sequences rather than audio, which means that our receptive field has gone times 64 without having to change anything about this model itself. That's the theory. In practice, it turns out that these code sequences are much harder to model than audio because they're much higher in entropy. They're much less predictable than audio. And so we found that this caused instability issues with VQVAE if you try to train this second level. So the bottom one is fine here, but if you try to train level 2 with a VQVAE, it actually gets very unstable. And the only way we found to stabilize it is using a trick called population-based training, where basically you train, say, 16 copies of your model in parallel, and then you're basically randomly jiggling the hyperparameters during training. And whenever one is sort of the worst off, you basically delete it and you replace it by a copy of a model that's doing well with, again, slightly modified hyperparameters. So you kind of get this evolutionary search over the hyperparameters while you're training your model. And this was useful here because most of the models would just diverge. And so PBT allowed us to then replace any model that diverged with a copy of a model that hadn't diverged yet. And we actually managed to train it to convergence that way. But obviously, it's quite an expensive way to train models because, if one of these models trains on 8 GPUs for a few days, obviously training 16 together gets quite expensive. And so that's why we looked at the argmax autoencoder, which unfortunately seems to always produce slightly worse results, but it's much less unstable, and you can just train a single one of them to convergence. And now I have some examples of audio generated with this hierarchical model. Before that, a few results from a human evaluation that we did, which is basically just me asking a bunch of my colleagues to rate a few samples from different models from 1 to 5. And so I asked them to rate the samples both on fidelity, which is just sort of the raw audio quality, and also on musicality, like how musical does this sound to you? Is it capturing chord progressions, is it capturing melody and things like that? And so we tried a few different models. The large WaveNet, the very large WaveNet is actually the model that I played you samples from before. So that one was already quite beefy and trained for a few weeks. And then we tried the naive way of extending the receptive field of this model, which is to reduce the number of units per layer so that we can fit more time steps into memory. And that's the thin WaveNet. With a large receptive field, still only about 3 seconds. That one did very poorly in the human evaluation, as you can tell. It's just not powerful enough to capture the structure of the waveform. And then we have our hierarchical models with 2 and 3 levels. And as you can see, the 3-level models there with the receptive fields of about 24 seconds do the best in terms of musicality. And there's no noticeable effect here in terms of fidelity, which is a little bit surprising to me because I feel like they sound a bit worse in terms of audio quality. They sound like they're being played through a 1920s radio, in my opinion. But that's actually expected because obviously it's a trade-off. If you're modeling more large-scale structure, you have less capacity to model the local structure of the signal, and so that reflects that's reflected in lower fidelity. So let me play you a few samples from a hierarchical model. So the quality isn't great, but it's sort of producing coherent melodies now. And it's doing all of this directly in the raw audio domain. So the model basically has no sort of explicit prior about what music is, other than that it's a waveform. I particularly like this one because it sounds a little bit counterpointy, and it's kind of surprising that the model has picked that up, because when you train a model on music scraped from YouTube, it's going to have a very heavy bias towards Chopin, romantic composers, because that's just what you find on YouTube when you look for piano music. But there was some Bach in there as well, and it seems to have picked up on that particular mode, which I thought was cool. In the interest of time, I'm not going to play any more, but you can find all of these online, including some 1-minute samples if you're interested. To wrap up, we have some follow-up work out on arXiv right now, where we apply these same ideas of sort of hierarchical autoregressive models on images. It turns out if you just try to apply what we did for music on images, it doesn't work at all. So you need a few new tricks to make it work there as well. And we're going to try and backport these tricks to audio as well. That's ongoing work. So these are some samples from hierarchical autoregressive models with 3 levels at 256 by 256. Yeah, and that's about all I have. So there's a blog post, the original blog post about WaveNet on the DeepMind blog there. And then I'll take some questions if you have them. Thank you. Yes.
First, congratulations. It's actually
I don't think your microphone is working.
That's a lot easier.
Yeah.
First, congratulations, absolutely stunning. I'm not entirely sure if your goal is to get musicians to get out of a job, but that's a really beautiful way of getting there, even if that's hopefully not happening. You started talking about symbolic representation of music, and I get the impression that it would be a really good first step for your hierarchical model. I'm assuming everybody has suggested that.
Yeah, we actually did that. I should really add a slide about that because this question comes up now and then. I just haven't had time to update this deck. I mentioned the collaboration with the Magenta team in Mountain View before. So we've had a few other collaborations since. And one thing we've done is we found this data set that has about 200 hours, I think, of piano recordings where both the audio and all the key presses are recorded in sync. And so this allows you to train a model that basically goes from a MIDI, a high-level representation, directly to audio. And this works really well. And we did that in a recent paper, which is actually going to be presented at iClear next month. The paper's called Maestro. And the data set as well is publicly available now, so you can download that and play with it yourself if you're interested. And so there, the idea was to sort of, like, if we have this intermediate representation, what can we do with it? And so we can train conditional wavenets, like wavenets conditioned on key presses, and they produce realistic piano sounds, so that's really cool. We can also train really good transcription models. So Magenta have this transcription model that goes from audio to key presses or scores. and that is state of the art. And then another thing we can do is take that symbolic representation and try to model that. And there is a new model called Music Transformer that works exceptionally well for that, also from Magenta. And so we sort of threw them together in one paper and showed, like, these are all the things that you can do when you have this data available. Of course, that's really nice for a piano where we are able to get that kind of data. But again, for other instruments like guitar and maybe sort of like full band music, it would be much harder to do that, I think. And so there it's nice to have an approach where you can learn the high-level representations. There's a lot of hands here, and I know. Let's start over there.
Can you hear me?
I can hear you just about. Yeah.
Okay. First of all, thank you for the awesome talk. Really enjoyed it.
Thank you.
So I have two quick questions. First one, maybe I just missed this one, but in the population-based training, obviously the way that you do the final evaluation is human-based. So I don't quite understand how you select during training what is the best performing model, because you have to have some sort of metric to select, which are the architectures and the branches of the tree to continue. And then the second question, obviously there's flow-based models and auto-regressive models and sort of GANs, which are sort of like implicit generative models. So I wish there was sort of more collaboration between the three fields, because obviously they have a lot to learn from each other. The one really interesting thing that you mentioned about the sort of back propagation trick where you sort of ignore the quantization. Are you aware of any work where that has been translated into like the sort of GAN world or the flow world?
I think people have tried it.
Because obviously that's one of the big unsolved problems for using GANs in an LP, is that you can't back propagate it easily, and then as a result you need to use tricks.
So I can't think of a paper off the top of my head, but I'm pretty sure that people have tried using these sort of quantization bottlenecks in the context of GANs as well. But I don't know if it worked. I'm positive it's been tried though. To answer your first question, during PBT, what we're measuring is basically just the likelihood of the data under the model. And what we find is actually that these models are so prone to instability that most of them will just diverge, and the one that you end up keeping in the end is just the single one that didn't diverge. So they're just extremely unstable. I also tried scaling up the model, giving it a bigger encoder and a bigger decoder, and then even with PBT, I couldn't train them to converge because they would all just diverge at the same time, regardless of which hyperparameters I chose. But yeah, so it's just a likelihood. Okay.
This is a musical question. I couldn't really hear because the length of your clip wasn't long enough. But as well as having a tempo, does the pieces of generated music also have a time signature, like a structure of beat?
That's a very good question. So I think. So the Bach one that I played has a pretty consistent tempo, which is nice, which is sort of emergent, right? Because I'm not hard coding anything in the model to guarantee that. But it doesn't sound to me like it's on a consistent meter. Yeah. I'm not sure at this time how to address that. Maybe some kind of, so for the symbolic modeling that we did in the follow-up paper that I just talked about. We used a small music transformer, and it's based on the transformer model, which some of you may also be familiar with. But one key component of it is that it uses relative attention. So you sort of explicitly embed the distance to all the other parts in the piece, and that allows it to basically look at what happened before and sort of copy entire motifs and sort of slightly modify them and reproduce them. And that model seems to have a much better understanding of meter, even sort of advanced meter like like the Romantic composers like to use. So maybe incorporating that type of building block into these models might be a way of achieving that as well. Yeah, that's you. And then I'll go to the back.
First of all, thank you for the talk. So I want to ask about whether you see any feasibility on doing transfer learning on the models that you have trained to low resource music cultures, which may also not, for example, adhere to like the Western classical music things. Like, for example, if we want to try generating some oud music or star, is it more meaningful to start from guitar or just churn with more data and computation power?
That's a good question. I think, so to train any of these individual WaveNets, I used a minimum of about 50 hours of recordings. We haven't tried this on the music side, but on the speech side, we found that if we just have a lot of different speakers and we train a conditional model where we feed in sort of the speaker ID as a conditioning input, then we can train on much less per speaker, because obviously the model tries to generalize between the different conditional settings. And so that could be a way to train on these sort of less common modes. Yeah.
One last question.
Yeah, I also have a question about the training data. So in terms, when people are judging musicality, in your training data, did you choose a specific key to feed, or was it like, because it sounds good, so I assume the triads of the song is actually composing well? Is it something that your model does, or is it something that comes from your training data in a specific key?
So the training data was not curated in that way. It was basically just me going on YouTube and following recommendations for like long videos of classical music, because I didn't want to get lots of small ones, so I only got ones that are like an hour or longer. And they were not curated in any way in terms of composers, or like I just took what I found, and I ended up with, in the end I ended up with about 400 hours or something. Very unevenly divided over different composers, but there was definitely no selection based on like key or anything like that. I saw a lot of other hands, but as I said before, you can just email me or talk to me on Twitter, and I will do my best to answer your questions. Thank you.